Today we will discuss how timber columns are designed. The whole procedure will be explained with the help of a few problems. The first problem is to calculate the safe axial load. So in the problem, a column of 150 mm by 150 mm is given and it is said that it is made of any wood, that is plywood, and the column is having unsupported length 1.5 meter, 2.5 meter and 3.5 meter. That is, we have three different type of columns or three different length of columns given, and we are asked to determine the safe axial load. The general equation to calculate the load is stress into cross-sectional area. Okay, so we shall proceed with the first case, that is the column is of length 1.5 meter and the cross section is 150 by 150 and the wood type is any wood or flower. For the design of timber columns, we will be following IS 883. Okay, so 883 1994, the code is design of structural timber in buildings. So you have to download it and use. And for the design of columns, we will be following clause 7.6. Here you can see columns 7.6, and today we will be dealing with solid columns, that is 7.6.1. The basic procedure of design of column is to calculate the slenderness ratio of the given column, and based on the slenderness ratio we have to decide whether the column is short, intermediate or long. And once it is decided, we have the equation to calculate the compressive stress of the column, and select a suitable equation and get the stress. Then multiply the stress value with the cross-sectional area and thus you will be getting the load carrying capacity. So in this question, the first case is 1.5 meter column with 150 mm by 150 mm cross section. So first of all, we will calculate the slenderness ratio of the column. Slenderness ratio is S by D, where S is the unsupported length of the column and D is the least lateral dimension of the column. The details are available at the initial pages of the IS code 883. And like what is S and what is D, you can get it from the first pages of IS 883. So S is 1.5 meter. I am converting it into millimeters. 1.5 into 1000 divided by the least dimension. Since it is a square column, we can take it as 150 and then get the slenderness ratio as 10. As per the IS code, if the slenderness ratio S by D does not exceed 11, it is a short column. Here you can see it is 10. So our column is a short column. And for the short column, as per the IS code provision 7.6.1.1, FC is FCP. FCP is the compressive stress value given in the properties of the wood that is used, and all those properties are listed in table 1 of 883. We can just move to table 1. Here you can see the table 1 extends over a few pages. Here you have to find out any wood. Okay, here you can locate that any wood is there in table 1 first page itself, and the main properties that we usually need is the elastic modulus of elasticity of the particular material of wood, as well as the prescribed stress, particularly the compressive stress parallel to the grain. When we use the wood as a column, the load will be in the direction parallel to the grain. So you have to take permissible stress, compression parallel to the grain. There again you have three options: inside, outside and wet. Inside is the most protected area where the column is placed. Outside is subjected to wetting and drying, and wet is something immersed or something like that. So for the any wood, you have to select the uh, Young's modulus value 104.5, and you have to select, say, the stress value 10.4 for the inside location. If nothing is given, you can select any one among these three. Okay, so in the question, if it is not given, you can assume, and the values can be obtained from table 1. So from table 1 for any wood, I'm considering grade 1 of type of wood parallel to the grade inside location, and I got FCP value as 10.4. So for this question, I need only the FCP value for the short uh, column. FC is FCP, and thus I get FC value as 10.4 from table 1, and cross-sectional area is given 150 by 150. So the load carrying capacity is 234 kilonewton. Okay, now we are moving on to the next case where the slenderness ratio changes because the unsupported length changes from 1.5 to 2.5 meter, but the cross section remains same. So here the slenderness ratio is 2500 divided by 150, that is 16.67. We have to decide whether it is a short column or a intermediate column or a long column. So we can move back to ISATT 3, and here you can see if the S by D value exceeds 11, you have to check whether it is less than K8. So how can you get the value of K8? K8 value is given at the front pages of the IS code. You can just move back and see. Here you can see that K8 is having an equation 0.584 square root of E divided by FCP. E and FCP are the Young's modulus as well as the compressive stress value of the column material that is obtained from table 1. Okay, so we have already for the any wood we have got E value as 104.5 and into 100 is required. There is no such mention in the IS code, but you have to make it as 104.5 into 100, and then FCP value we got it as 104.5. Thus you calculate K8 value, and here it is obtained as 18.51. Now you can see our slenderness ratio 16.67 is between 11 and 18.5. That means it is an intermediate column. Now, since we have identified it as an intermediate column, we have to go back and get the equation to calculate the stress value of intermediate column. Here you can see FC is FCP into 1 minus 1 by 3 into S divided by K8 T raised to 4. So substitute in that equation. FCP value is 10.4 for any wood. Then S is 2500. K8 we have calculated it as 18.51, and D is the least lateral dimension 150. And thus I get FC value as 8.116. To calculate the load carrying capacity, what you can see is FC into A. Thus I get it as 182.6. You can see that for the same cross section, when the length increases, it becomes short column to intermediate column to long column. And as the column changes from short to intermediate to long, the load carrying capacity reduces, because in the first case it was 234, and when it becomes an intermediate column with the same cross section, its load carrying capacity is 182.6. Now moving on to the third case, that is the length of the column, unsupported length of the column is 3.5 meter. I am calculating the slenderness ratio again. K8 value is already calculated to be 18.51. My slenderness value is greater than the K8 value, hence it is a long column. Okay, so as per the IS code, S by D is greater than K8, it is a long column, and the FC value is calculated using the equation 0.329 E divided by S by D whole square. So I'm calculating the FC value. E is 104.5 into 100. S by D is 3500 divided by 150 square, and I get FC as 6.315, and I calculate the load carrying capacity as 142. Here again you can see that we have not changed the cross section, just the length, unsupported length increased, and as it changes from short to long column, the load carrying capacity reduces. So that's all for the first question. So the entire procedure is very simple. Calculate S by D. Based on this, maintenance decide whether it is a short, long, or intermediate column. Calculate the FC value. Get the material properties of the wood from table 1 and calculate the load as stress into area. Now moving on to a similar question, but here the column is a circular column. When you are using a circular column, you have to get the least lateral dimension, or the dimension is to be obtained by equating by considering an equivalent square cross section. So my second question, the column is 150 mm diameter. The effective length is 2 meter. We have to find the safe axial load, and it is given that the column is in an outside location, uh, subjected to alternate wetting and drying. It is not continuously wet, but alternate wetting and drying, and outside location. So since it is a circular column, I have to equate it to a equivalent square column. So I am equating the area of circle to area of square. That is pi by 4 d square is d equivalent into d equivalent. Thus I get the equivalent square dimension as 133 mm. Now I will be proceeding with the 133 for the further calculation. I'm going to calculate the slenderness ratio. The span of the unsupported length is 2 meters. So 2000 divided by the equivalent dimension 133 gives 15.03. So it is greater than 11. So I definitely have to check it with K8. So K8 value equation get from IS 883. It is 0.584 root of E divided by FCP, and E and FCP value for the wood has to be calculated. The type of wood has to be adopted is not given in the equation. I mean in the question. So I am assuming a teak wood, and I am taking the properties of teak wood from IS code. Say in IS code, I have to go back to the table where I have to locate the teak wood. I have already located it in the place, say in this page. You can just go through and get the teak wood. Find. Okay, fine. This is T code. The E value is 99.7, and the outside location I need outside location FC value. Outside location FC value is say 9.2, right? Okay, so let me check. T code 99.7. Yes, I have adopted 99.7, and let me see the FC value. Here outside location it is 8.3. Yes. So it is 8.3. It is correctly written here. So I have to calculate K8 as 0.584 99.7 into 100. Don't forget to put the 100, divided by 8.3. Thus we get 20.24. So my slenderness ratio is like plus than 20.24. So it is an intermediate column. For the intermediate column, I know the equation from IS 883. Go back to 7.6. 7.6, and for the intermediate column, here you can see the equation FCP to 1 minus 1 by 3 S by KHD all raised to 4. So I am substituting and get the value of FC as 7.457, and I am getting the axial load carrying capacity as a stress value into cross sectional area. Here, cross-sectional area, you can either put the cross-sectional area of the circle or the equivalent square, because both the areas are equated, so both will be same. So 7.457 into pi by 4 into 150 square will do. Or 7.457 into 133 into 133 also will give you the same answer. Okay. So that's it. The same procedure. Calculate the slenderness ratio, identify the type of column, and get the value of stress as per the equation suggested in IS 883 close 7.6. Then calculate the load as stress into cross-sectional area. Moving on to the third question. Here we have to design the column. The column carries 500 kilonewton. The effective length is 3.5 meter. Design the wooden column. Inside location and select grade wood. Type of wood is given only as select grade. So P and S are given. Maybe we can have different type of assumption. So in first case, I am assuming that this is a short column, and I am deciding the cross section based on that. So here you can see, since I am assuming it to be short column, S by D should be less than 11 as per IS provisions. Here, since it is a short column, S by D should be less than 11. So based on that condition, D should be greater than uh, S by 11, that is 3500 by 11, and I get 318. So if my cross sectional dimension is greater than 318, I can design it as a short column. So I am taking it as 320 as the type of wood was not given. So I am taking hoppe wood, that is Tambadam, and I have to get the properties of that hoppe wood. And I am moving on to the particular page, and here I have to find the hoppe wood is there. Two rows are there, you can select accordingly. Say 147.9, and for inside location 14.5. 14.5 and 147.9 are there. And for select grade wood, there is a special clause that you need to remember, that is in 6.3. So we have to go to 6.3. Say 6.3 is available in, okay, 6.3 I have reached. Here you can see, for select grade, you have to multiply the stress values with 1.16. If it is grade 2, you have to multiply the stress values from table 1 with 0.84. So since it is select grade, I am multiplying FCP with 1.16, and here you can see that I am getting the stress value as 16.82. Okay, then I am calculating the S by D value 3500 by 320, that is 10.93. I was just checking whether I am getting the short column itself. Then I have calculated the FC value as 16.82, and I have calculated the load carrying capacity as 1722. Actually, I needed to carry 500 kilonewton, but since I have chosen Tambadam, it is having 1722 for the required cross section. Load carrying capacity is much greater than expected. When I move to intermediate column, I assume that the column is intermediate. In that case, what happens? I get that D should be less than 380. So I select 300, proceed with the same procedure. I get E and F value, same as previous case. Then I get, for the selected, I get the FCP, and calculate the K8 value as per the model provision in this page number 7.6.1.2, and I calculate as FC value for the intermediate column, and then I take the column. Then I take the column as column load carrying capacity as FC into A, that is 1409. So it is quite simple. First of all, you decide whether you need to decide it as a design it as a short column or intermediate column. That is your choice. If you design it as a short column or an intermediate column, what happens based on that? You will get the properties, and you end up with the calculation of axial load multiplying stress with area. Now we can see a question from the question paper. It is quite simple. It is given that it is a sandwood with cross section 200 by 200 and unsupported length 5 meter. Find the safe axial capacity, load capacity. For 5 meter and 200 cross section, S by D is 25. It is greater than 11. So I need to check it with K8 value also. I have checked it with the K8 value, and it is found that K8 value is only 20. So it is a long column. Our S by D value is 25, K8 value is 20, so S by D is greater than K8, and hence it is a long column. And when it is a long column, you have to adopt the equation to calculate the FC for the long column, that is 329E divided by S by D square. Thus I get the FC, multiply FC with the cross sectional area to calculate the what the axial load carrying capacity. So these are the type of questions asked for solid columns. The entire procedure is quite simple. You just need to find S by D, that is length ratio, to decide whether the column is short, intermediate, or long. Once it is decided, based on the particular criteria, calculate the FC value, multiply FC with cross section to calculate the axial load carrying capacity. That's all. Okay, so that's all for today. Thank you.